So now that we understand information visualization and information visualization systems, we can start to use them to visualize data held in databases, and we can use them in concert with data mining.
So often when we visualize data, the data is going to come from a database, and it'll be quite useful and effective if during that interactive visualization session when we're trying to investigate data for our own purposes and gain insight into the data, if we can connect the tools for visualization into queries to that database so that it's easier to dig deeper into the data directly. So there are databases that support this. Often modern databases support OLAP processing, online analytical processing, which basically allows them to be accessed over the web using standard protocols. And conceptually, a good mental model for the data is this data cube metaphor. And if you have, for example, a sales database that represents the amount of sales on a given date of a given product at a given location, then you can think of the keys to that data set, the date, the product, and location, as dimensions of, for example, a cube here. So each row of this data corresponds to a cell in this data set. And so if the date is the horizontal axis, the product is the vertical axis, and the location is the depth axis in this cube, then you've got three coordinates that gives you a particular cell in this cube, and that cell will represent the amount of sales at that date of that product at that location. The challenge is going to be taking this data set and visualizing it. I'm using an example of a cube with 3 dimensions, and we're used to perceiving 3 dimensions, but we perceive 3 dimensions by projecting it into 2 dimensions and looking at that. In real-world applications, you're going to have many more keys, and this data cube is actually a data hypercube, and you'll have many more than just 3 dimensions of data. And the challenge is going to be taking this high-dimensional data space, this data hypercube, and then finding the appropriate 2 dimensions in which to investigate, and then you can always add more dimensions as glyphs or other visualization tools. So the way we're going to reduce the dimensions of the data set is going to be largely with data aggregation, and there's a large number of database visualization tools based on data aggregation. The common ones like Tableau or SAP's Lumina, or even the pivot tables that are available in Microsoft Excel are based on data aggregation as a way of simplifying a data set and reducing the dimensions of variation by providing summaries of the data. So, for example, here's some data. We're plotting some quantitative value vertically as we change some other quantitative value horizontally. We've got an independent variable here and a dependent variable here. This is a 2-dimensional plot. We could always project this onto a 1-dimensional axis, and we can also summarize this data. These would be values. These would be measures changing across one axis into a single value by representing it by the mean value or the maximum value, the minimum value, or the sum of these values. The mean is just going to be the sum divided by all the values of the dimension of the dimension. And so we have various operators: sum, mean, median, minimum, maximum. There's other statistical operators like standard deviation or variance or other characteristics you can use that will simplify data and basically remove one dimension. In this case, removing the change in value over one dimension to a single value over no dimension. We can also convert quantitative continuous data into quantitative discrete data or ordinal or nominal data, and the count function does that. For example, if we have these blue, red, and green data points, there's 3 categories here. They're being plotted over a 2-dimensional area that's going to represent continuous quantitative data horizontally and vertically. We can then remove those axes and just have a single axis representing the count, the number of blue items, the number of red items, and the number of green items. and that reduces the dimensionality of this data set from varying over 2 dimensions with a third category into just a category over essentially one dimension. And finally, there's binning. And binning is a discretization method that converts quantitative continuous data into quantitative discrete data, or ordinal or nominal data, depending on how you use it. For example, we may have our continuous function. These are values that are varying over a single dimension. And instead of having these values represented continuously over a continuous dimension, we can discretize this dimension, and then we have our quantitative variable that's being sampled on 4 regions and represented by the in this case the mean value over those four bin areas. And so we're doing a projection operator over in this case over 4 areas instead of over the single area. But again, that does reduce the dimensionality of the data set. And finally, we can use this to create a histogram. And a histogram is binning, in this case, in the vertical direction instead of the horizontal direction. So instead of having bins over the dimension, you're having bins over the value that you're plotting over that dimension. In this case, we've separated the values into an A, B, C, D, and E range. And then we're adding up all the values in the A range, all the values in the B range, all the values in the C range, and all the values in the D range, and just plotting those sums. And there's no values in the E range, so there would be it would be 0 for the E range. And so this histogram, when you choose these buckets, the size of these bins gives you other characteristics of the data that can reduce the dimensionality of the data, or at least reduce a continuous variable into categories of a discrete categories of a continuous variable. And so our data cubes can use these aggregation operations to simplify a data set. And that provides a useful tool for investigating the data set. So, for example, we can take our data cube. In this case, it has location horizontally, products vertically, and time in depth. If we, for example, if we want to look at all of our sales of tea, coffee, espresso, other products over time at different times, but we don't care about the location, then we can project this data cube into basically this square region, this two-dimensional region. So this is a two-dimensional projection that's summing up all of the sales at any given time of a given product regardless of location. So it's summing them up over all the locations, and that projection gives us something we can then visualize. We can further summarize that, projecting this two-dimensional data cube into a one-dimensional data cube by summing, in this case, over product. We don't care about the differences of the products. If we don't want to differentiate the product, we can aggregate the product axis, sum over that, and now we have a one-dimensional, basically just a list of numbers that tells us the amount of sales for the first quarter, second quarter, third quarter, or fourth quarter. And if we don't care about the time, then we can just look at the total sales over a given amount of time, over a given set of products, over a given set of locations, add all of those up, and that gives us this zero-dimensional data cube here. So here's an example using Tableau to show how aggregations are used for data cube operations. Here we have some dimensions of our data. The data is collected over 10 years, and so we have separate data by year and over a variety of different countries. And then we've got what I'm showing here is our standard method for plotting population logarithmically horizontally over life expectancy vertically. And you'll see that we're averaging the data, and we have a single data point. We basically have zero-dimensional data. It's all being projected to a single point because we're averaging over all these dimensions, specifically the time dimension over all the years that we have data and over all the countries that we have data. If we want to disaggregate this data, then we can do that by basically dragging into this marks area, for example, country. And now we we spread out the data, each one of these data points represents a different country, so that these averages are just averages over the year that the data is collected on, and not over the country and the region. We can further disaggregate over the year, and we get this plot, which shows you for each country how it's changing over the year. If we want to see correspondences between countries, then I can drag the country into color so that each country gets its own color. So you can see how the colors are. You can use the color to follow the country over the year as it's been disaggregated. And we can start adding more and more dimensions from our data cube into this visualization. So when you're looking at an individual cell of these different forms of data cubes, you can work from a less detailed view to a more detailed view. A single cube, when it's averaged, could represent a range of products, a range of locations, a range of times. Or it could represent the value in a specific location at a specific time. And this is in its disaggregated form. It's representing an actual data point. In its aggregated form, it's representing an aggregate of the values over these ranges. So these could be the total sales of all products over all markets over all time. And then you can start to drill down to these details by basically focusing, for example, on a particular instance of time, or on a particular product, or on a particular type. And each time you do that, you're replacing an aggregated dimension where you have a single value representing a range of one of these dimensions with a specific product or a specific data point along that dimension, a specific coordinate along that dimension. And so by doing that, this data cube approach allows you, while you're performing your visualization, to be able to drill down into details and to back out into more summary views.